Good evening, ma. Till now we were discussing about the conditions for any of the reaction turbine to have a maximum efficiency. Why do we calculate all this? If we do some work, we try to gain the maximum efficiency, right? We are working to have a more work done, right? For this, till now we have derived the relation for the blade efficiency as well in order to get the maximum power output. Now, what would be the condition? In the previous class, we have seen the relation for the blade efficiency to be of 2 times of whole multiplied by 2 times of rho cos alpha minus rho square divided by 1 minus rho square plus rho cos alpha. 2 times of rho cos alpha. When we will have the maximum power. Whenever the denominator is less, then we can get the maximum efficiency, right? The condition. What is the condition we have here? For the efficiency, what is the condition we are trying to find out? The efficiency to be maximum, right? When can we have this efficiency to be maximum? When the denominator 1 minus rho plus 2 rho cos alpha is minimum. You can have the blade efficiency to be maximum. This is the condition, right? Yes, ma'am? Now, still further moving to find out the other parameters, like when can we have the maximum efficiency and what would be the relation? I said minimum. What is the minimum value to be there? For that, we find out the denominator, how it can be calculated. Now, if you look at this equation, 1 minus rho plus 2 rho cos alpha, take this equation and differentiate it. Then I can say that d by d rho in terms of 1 minus, sorry, here it is p square, rho square, 1 minus rho square plus 2 rho cos alpha. Right, ma? Yes. If I differentiate it, it has to be equals to 0. Now, if I differentiate it, minus 2p plus, 2 rho minus 2 rho plus 2 cos alpha equals to 0. Then rho equals to cos alpha, or what is this rho? Since rho equals to u divided by v1. What is this u divided by v1? It is nothing but blade speed ratio. Blade speed ratio. Or you can write it as u by v1 equals to cos alpha. That is u equals to v1 cos alpha. Under this condition, if I substitute it, I can get the value of maximum efficiency, right? U equals to VW1, right? It is again, what is VW1? V1 cos alpha, and the value VW2 should be 0. The relation between the blade efficiency and the blade speed, we can get it from the previous derivations, right? And now, if I write this relation and substitute the value of rho equals to cos alpha in the third equation. For that only we are trying to write the condition to have the denominator to be minimum, right? Now, maximum efficiency equals to 2 times of maximum efficiency equals to 2 times of cos square alpha minus cos square alpha, right? Whole divided by, just 1 minute now. I will erase these brackets so that there will be no confusion. I will write it here clearly. 2 times of 2 cos square alpha minus cos square alpha whole divided by 1 minus cos square alpha plus 2 cos square alpha. I am trying to simplify this expression. If I simplify it, if I open the brackets and simplify it, automatically here I will be coming up with an expression 2 cos square alpha divided by 1 plus cos square alpha. Right? Again, if I want to simplify it, sin square plus cos square alpha equals to 1. I can get it in terms of again sin square alpha. Right? Still I can simplify it. If you want, you can leave as it is here, or still you can simplify it as 2 times of cos square alpha by sin square alpha. Right? And still further it can be written as 2 times of tan square alpha as well. This is the expression to have the blade efficiency to be maximum. Now, put it in the simple form. Maximum efficiency equals to 2 times of tan square alpha. Right? This is the expression. Now, what is this alpha? Alpha equals to outlet angle of fixed blade. Outlet angle of a fixed blade, or you can call it as an exit angle, or exit angle of fixed blade, or exit angle of a fixed blade. Right? These are all the conditions that we have to remember before getting into the problem statements of any of the reaction turbine. Right? And now take time to recollect what are all the things that we have discussed under reaction turbine. Right? And just shall we have a quick recap on this? We have derived the relation for work done per second, and the expression is in terms of m multiplied by VW1 plus VW2 into U divided by 1000 kilojoule per second. That is the first relation we have derived for the reaction turbine. The second one is power developed. Power developed, the relation, what you have the relation here, the same that of the work done per second, but the units will be changed. It is represented in terms of kilowatts. That is m into VW1 plus VW2 into U divided by 1000 kilowatts. Right? And next we have come up with another new topic, degree of reaction. What would be the degree of reaction expression for a reaction turbine? It is given as the ratio of enthalpy change over a moving blade to that of a total enthalpy in the entire stage. And we have derived the relation to be of VR2 square minus VR1 square divided by 2U times of VW1 plus VW2. Right? With this condition, with this relation, we have derived the relation for Parsons reaction turbine. What is the Parsons reaction turbine here? What is the value of a degree of reaction? We have solved it one after the other by considering the enthalpy drop over a fixed blade. and enthalpy drop over a moving blade, right? And finally, we have concluded, or we have got a relation of 1 by 2. That means here the Parsons reaction turbine has a symmetrical blade. That is that a fixed blade and the moving blade, both of them are symmetrical about its central axis. So the equal distribution of the pressure is there on both the moving as well as the fixed blade. Right now, that is the reason. Like we say that if any of a turbine has a degree of reaction of 0.5 to a range of 0.6, we call the turbine as impulse reaction turbine, right now? And the next one we have discussed is about a blade height, and how we have calculated the blade height by taking this volume of a flow into consideration, and it is given in terms of flow area and to that of a velocity of a flow. And what is the relation we have here? Volume of a flow is given in terms of pi into d suffix m into h into v suffix f, where d suffix m is nothing but the mean diameter, and h is the blade height, and v suffix f is the velocity of a flow. And from this relation further we calculated the mass flow rate, and the mass flow rate is given in terms of pi volume of a flow divided to that of the dryness fraction in terms of specific volume of the steam for that given section, right? And even this h by d means like is the height of a blade, and d is the diameter of a wheel. What is the relation between the mean diameter and the diameter of a wheel? Whereas the mean diameter is the summation of the height and the diameter of a wheel. From this, like h by d is taken into consideration as a constant, and that constant value is represented with a k, and it is equal to that of 1 by 12. Yes, and after this we have gone for the deriving the relation for steam flow rate in terms of k. The same mass flow rate in terms of k, and we have come up with the two cases, case 1 and case 2, where m is expressed when it is not full, and m is also calculated when the entire flow is occupied over the entire nozzle and the blade annulus, right? And for this also we have got two relations, and after that we have started deriving the relation for the maximum efficiency of a reaction turbine, right? And what is the expression we have here for the any of a condition according to the velocity diagram? And according to the velocity diagram, we have considered the total energy supplied. What is the efficiency relation? Efficiency relation is nothing but the work done to that of the energy supplied. Already we had the expression for the work done. Now what we are supposed to find out? We are supposed to find out for the entire stage. For the entire stage, what was the total energy that we are supplying? Entire stage means here we have two blades. One is the moving blade and another one is the fixed blade. Then we need to calculate what is the energy transfer or the supply to moving blade and what is the energy supplied to that of the fixed blade. If I am able to get the energy supplied to that and I substitute it in the ratio of efficiency of a blade to be of work done to the energy supplied, I will get a relation of 2 times of 2 multiplied by that of 2 rho cos alpha minus rho square divided by 1 minus rho square plus 2 rho cos alpha. This is the expression for any of a blade efficiency. If I want to have a maximum blade efficiency, maximum means the denominator should be minimum. When can I have the denominator to be minimum? If I differentiate it, then I'll get a value in terms of u. And if I'm going to replace that values of u and simplify it, I'll get the relation for the maximum efficiency in terms of 2 times of cos square alpha divided by 1 plus cos square alpha. Here I have written 1 plus cos. This is totally wrong here. What I have expressed here, it is wrong or right? Tell me. I said wrong, but I have written something else here. Can I consider this value? Yes. 2 cos square alpha by 1 plus cos square alpha. What sin square alpha plus cos square alpha equals to 1. In place of like, now. What I did? Sin square alpha plus cos square alpha equals to 1. If it is of 1 minus cos square alpha, I can write it as a sin square. That is the reason why I am saying that I have written something wrong here. Right? Sine square alpha, that I cannot write it. If it is of plus, I can write. Therefore, here I have to substitute the same value. 1 plus, just I'll change the color so that whatever the correction I have made here will be clear for everyone. Right? Here I'll write this. 1 plus cos square alpha. This is wrong. Now, what is the relation I have here now? Final relation for the maximum efficiency. Now, it is 2 times of cos square alpha divided by 1 plus cos square alpha. Right? And here the alpha is nothing but the outlet angle of a fixed blade, or even you can call it as the exit angle of a fixed blade. Okay, ma? Thank you. And in the next session, we will be doing some problem statements with this knowledge. Okay, thank you.